Tad lūdzu, Andra, tad jums vārds par savu zinātnisko virzienu. Iepazīstiniet mūs visus. Lūdzu.
Jā, tūlīt es ieslēgšu. Vai var redzēt?
Jā, viss skaisti redzam.
Vai tā tūlītās? Hello, my name is Andra Blumberga and I work as a tenure professor at Riga Technical University, Faculty of Natural Science and Technologies in the Institute of Energy Systems and Environment. And I will just talk today about one of my research topics, which is energy transition towards energy neutrality. And I would like to start with my curriculum vitae. Before I started my academic career at Technical University, I worked for almost 10 years as a head of the ventilation department at international technology company ABB Latvia, and also worked for more than 6 years as a managing director in a local energy consulting company, Ecodoma. My Hirsch index currently is 23. I have 155 publications in Scopus database. I have supervised 12 doctoral theses and they were defended also. I currently supervise 6 doctoral theses, and I have supervised 47 master theses and 28 bachelor theses. I give lectures in courses Energy Efficiency of Buildings, System Dynamics Modeling, and Environmental Policy and Environmental Economics for environmental engineering students at Riga Technical University. I have a vast experience in participating in various projects, research projects. I've been a project leader and executive participant in many national and international projects, and it's just a few of them that were mentioned here. And just at this very moment, I'm a project coordinator of the leading partner in one of the two Horizon projects going on currently in the institute, and also involved in a national research project about national climate and energy modeling. Just before I tell my own experience, just to give some background what energy transition is and why it's so important. And it's from the social technical transition theory that there is a current system state, and it's called pre-development stage. And then when the transition starts, then there is an acceleration phase, and there are some hopes how the transition will behave over time. And we have a fantasies that it will be either fast or more slow and so on, but it will certainly go to the direction that we hope it will be a positive development. But in reality, as you all know, things do not happen the way we expect, and there might be where the system develops and stabilizes, there can be lock-ins, then can be backlash, and in the worst case, there can be even the breakdown of the system. And which direction the system will go depends on many different factors. And energy system being a complex systems with many technologies, humans, companies, economies, climate, and so on, having multiple feedback loops, multiple delays, and non-linearities, these energy systems is a good example of how complex systems behave, and we can see unexpected behaviors over time, and so we have to think how we can change the behavior of the system. What energy transition is, it's worth to study and to deal with, is that because the systems are super complex, many policies are counterproductive. People cannot perceive complex and dynamic systems because our mind is too simple. And we can often see that short-term solutions can lead to unpredicted long-term consequences. And people have a tendency to blame external forces rather than look for the roots in the system itself. The effects of feedback loops can lock a system into unsustainable behavior. And a public or general public or lay people can be dissatisfied with the policies because of unintended side effects of the policies. And of course, we cannot find even a single policy scenario that has no pressure or stress, but it is possible to find alternative solutions, and some of them are more desirable than others. So my research is dealing with two aspects of energy transition. And one is more related to laboratory research and the development of different technologies related to energy efficiency in buildings. And I am head of energy efficiency laboratory in our institute, and we have a laboratory facilities. And the other research direction I'm involved is system dynamics modeling, and I will just shortly provide some short insights in what I'm doing and what my group is doing. First is energy efficiency technological solutions, and we've been doing many things over last decades. And just to give some glimpse on it, it's the one is internal insulation of historic buildings, and I will shortly show in a minute just a few results from Horizon project we had together with partners from other EU universities. And we also work on other issues, and for example, climate adaptive building shell based on biomimicry technology to reduce indoor CO2 reduction. And of course, all my research activities are described and published in different various papers. Just to give an impression of what we do in our lab for energy efficiency in buildings, here is the web page of one of the projects we had. It's called Rebuild. It's internal insulation of historic buildings. It's a large building stock and which needs internal insulation, which is a complicated issue due to hydrothermal behavior of the walls, which changes when you apply internal insulation. So what we did in the project, we did a modeling. Here is on the left-hand side, there are some pictures from the models. We did the measurements and tests in the laboratory, and we also did in situ measurements in real buildings where the internal insulation was applied. We also did some laboratory research. We collected 40 historic brick samples from all over Latvia. We tested these samples, and then we used the data obtained from these tests. We used for mathematical simulations. And here is just an example of capillary active insulation system applied to different types of bricks. And you can visually see that the results are very different for different brick types. We also model different insulation systems and the way they are applied. And here is an example of the same capillary active insulation system, calcium silicate, how the gluing process has an impact on hydrothermal behavior of the insulation system and the whole wall. The other research direction, as I already mentioned, is system dynamics modeling, dealing with complex nonlinear systems with feedbacks and delays. And the approach is that usually we can, the people perceive reality based on events, which basically we can see as some just the names in the news articles or some news portals, which does not say anything about what are the causes of different events. Behavior is the parameters that are changing over the time. So it's a graph over the time, behavior over the time. And the structure is mathematical models describing reality, which can generate the behavior, which then generates events. And so we built and we discovered the structure, how the reality functions. And I will just show you a few examples of this modeling approach. One is we are currently also involved in developing national energy and climate policy modeling tool. And this is in Latvian. It's a national energy model we did a few years ago for the national government, and we are doing also now. It's about energy supply sector, heating and electricity, and all the demand sectors, including households, industry, tertiary, public transport, and also agriculture sector. The way we explain and we deal with this modeling, this is just a causal loop diagram showing complexity of energy systems, how the energy demand is related to energy supply, and what are the driving feedback loops driving the behavior of the system. This is a stock and flow diagram of the modeling approach that we use, and this is just a visualization, and with all these little round circles and these boxes, there are equations, mathematical equations hiding behind this model. And for the end client or for the financing institutions, we normally do not show the stock and flow diagram or the causal loop diagrams we sometimes show, but we develop online interfaces. And here is just an example of online interface for different policies and different outcomes in the form of graphs as a behavior. So the policymakers can play with the different policies and see the impact of the policy measures. This is how the policy scenarios are developed. So the policymakers can play with different policy sets and see what the impact will be on the final results. Then just quickly showing example from this research on the national policies. This is something that we show for the last almost 25 years. I always show it's called shifting the burden to intervener. And there is the energy shortage in the middle, and there are two options. When we have energy shortage, we can either go to the left-hand side, which is a short-term solution. Normally, it's like a fossil energy sources. So if we need energy, we just call a natural gas company and ask to increase natural gas flow. And the more the short-term is used, the less the energy shortage there is. The other option is to use long-term solution, which is a renewable energy source and energy efficiency, but there is a delay because we need time and we need resources to go for this long-term solution. So people normally tend to go for short-term solution, which is the end develops. There is a delay. The more you use short-term solution, the less the long-term solution is used. And we are caught by addiction loop. It's called addiction loop. And so with the natural gas in Latvia, we saw the strengths of this addiction loop when there was this energy crisis back in 2021. And also currently being discussed other depletable resources such as nuclear power or coal or other, which again will catch us in this addiction loop. So we should discuss to go for the long-term solution instead of short-term solution. Then we also study different internal dynamics in the systems, and here is an example of energy efficiency sector in the household sector, how the oscillations of financing create unintended consequences for pricing and payback time, and how the supply and demand of the market, construction market, has an impact on the energy efficiency national goals. Then quickly, just energy communities. I also deal with energy communities. We have built a system dynamics model to study energy communities. Here is just the technologies that we have in the model, and we have applied this model to different places already. It's an urban block with in a historic city center, in university campus, in multi-family buildings. So there are many different applications, and I have a number of papers also published on this topic. This is just an example of an interface for single-player game for energy community. We also have developed multiplayer game based on Prisoner's Dilemma. to be applied to build energy community. And we also have developed policy making tool for policy makers who deal with energy communities and policies for energy communities. I'm involved in multidisciplinary research, and I think this is where energy research should go and join social and humanitarian research. And it's just an example where we studied hard to reach energy users together with Latvian, with Estonian, Swedish, and Norwegian colleagues. And just to understand who are hard to reach energy users, how they are different from other energy users, and how different they are from experts. And you can see just visually that on the left-hand side, they are hard to reach. And you can visually see that the mental models are really, really different from other two groups. And finally, to conclude, I will just show just one slide on the massive open online course I have developed for students, where all the knowledge from the previous research in energy field is used to teach students on energy transition and climate change. And it's basically based on system dynamics and system thinking approach with all this feedback loops, complexities, delays, and non-linearities. Okay, thank you for your attention.
Okay, thank you very much. Now it's open for questions. Could you please take away this? Okay, I could see. Okay, Anders Ozols, as usual, is very interested in this field. Okay.
Yes, indeed. I'm interested in Andra's presentation and very fascinated by her words that she has investigated complex nonlinear systems with feedbacks and delays. Indeed, these type of systems are most widespread. And in this respect, I have two questions. First, I did not see any mathematical expressions. Can you please show any mathematical expression which you have used to calculate these systems with nonlinear systems with delays and feedbacks? What type? Integral, differential, and so on? Can you show at least one of your mathematical expressions, if you have used many, of course.
Yeah, I'm not sure if I can do it, because on the computer that I'm running now, I don't have the software. It's on my laptop, then I have to switch computers. Then I can open and show you how the modeling is done. What else I can do? I can show you just from I can quickly try to open.
If it takes more time, only maybe some words. Are these systems of integral differential equations, or
yes, it is.
Such equations do you treat, and so on?
Yeah, this is it's about stocks and flows. Stocks are the things, are the places where parameters are integrating. So it's about integration, how the things are accumulating over the time, and the flows are the derivatives. So we study inflows and outflows that change the stocks, the values of the stocks. So there is an integration, and then we use other variables just to explain how these stocks are changing, why the stocks are changing. So these stocks and flows become part of feedback loops. So that's the way.
Yes, I understand, but you all have described it mathematically.
Yes, of course.
And solving it by a computer.
Yes.
Okay, nice.
Yes, we use a software tool called Stella Architect. That's the software we use.
And another question is about climate. Surely that climate is just such complex nonlinear system with feedbacks and delays. And previously in Senate meeting, I asked you about climate forecasts. So, and you told me that we believe in some, I think, 300 scientists who have made such calculations, and they predicted that we should decrease CO2 and so on. So my question is, did these scientists, about 300 or something like that, also made such type of calculations, or these are merely only qualitative predictions in this respect? Thank you.
Yeah, I'm not sure. I know that there are modelers who use also system dynamics approach also. I know these people, like they work for United Nations Environmental Program. They use system dynamics models, which of course are mathematical models. I haven't studied in details how they do the modeling for climate, like climate researchers, how they do it. I don't know, because I'm not from the climate research, like a climate. So I don't have a comments on that.
Thank you very much.
Okay, thank you. More questions? I don't see. Thank you once more. I see that this is very interesting topic for science and also for politics and so, and I hope you will be a full member of Latvian Academy of Science, and then we will be able, as a member of the Academy, to give the view of academy in also politics. Thank you once more.
Thank you.
Okay, now we could move to next point in our today, and that is our foreign member candidates. And I would like to ask as ladies the first, and maybe Alma could start and tell us.
Thank you.
Thank you. Please take a screen.
Окей. Сейчас скажу, который у нас был экран. Вот это. Окей. Здесь, наверное, F5.
Okay, we see.
Вот это.
Thank you. Go ahead.
Лучше F5. Нажмите. Full screen, yes.
We can't hear.
Oh, okay.
Okay, okay, now it's okay.
Can I begin?
Yeah, go ahead, please.
Звук включен? Звук включен, yes. Okay. Labidien damas un kungi. I will now briefly introduce my research and pedagogical activities. From 1971 and 1983, I graduated from Kazakh State University in Almaty with a specialization in solid-state physics. Afterward, I pursued postgraduate studies at the Kazakh Pedagogical Institute and completed my research at the Institute of Physics of Estonian Academy of Sciences, at the laboratory of Czeslaw Lushik, where I defended my candidate thesis under supervision of Ariadna Erlanga. From 1983 to 2005, I worked as an associate professor at the Satpayev Kazakh Polytechnic Institute. Since 2005, I have held a professorship at the Gumiļova Eirāzijas National University. My scientific research areas: solid-state physics, studies of defects induced by ionizing irradiation, modification of materials by swift heavy ions, study of radiation resistance of materials, track technology, template synthesis of nanovirus. My pedagogical work, under my supervision, defended 20 bachelor's theses, master's degrees, 6 candidate theses, prepared and defended by Zdarovets Maxim, PhD's degree 10, currently in the preparatory stage, doctor's degree for PhD students jointly with Latvian scientists, 3 PhD students. Also, you can see my awards. About my projects. The number of projects in which I have served as either project leader or principal investigator from 2013 to 2024 is approaching 13. Project research tasks. First, the main task is to study radiation damage in radiation-resistant materials irradiated by swift heavy ion, which model the nuclear fuel fission fragments. Second, track technology related to creating track templates based on silicon dioxide on silicon substrates for the formation of nanovirus and nanoheterostructures. Third, modification of material properties by ion beams. The history of collaboration with the Institute of Solid State Physics dates back to the previous century, with a new phase beginning after Kazakhstan's independence. Near our university, the DC-60 ion cyclotron was built. It's the building of our university. Here you can see the channels of our cyclotron. The invaluable support of Professor Kurt Schwarz facilitate the development of material modification using ion beams, enhancing our capabilities in this field. Let's review some of our results. On this slide, you can see the silicon dioxide on silicon substrate structures were irradiated with 200 MeV xenon ions up to fluence 10 to 8 ions per square centimeters. Then the tracks have etched in hydrofluoric acid aqua solution, creating nanochannels, which we subsequently filled with different materials using chemical deposition and electrochemical deposition. You can see the fillet structure. In this case, we fillet the nanochannels by oxide semiconductor tin dioxide. And we obtained the nanovirus of tin dioxide with orthorhombic structure. The structure of this nanovirus were calculated by Alexander Platonenko and Sergei Pivskunov. Also, we measured the photoluminescent properties of these structures and electrophysical properties. The next slide shows our investigations of radiation resistance materials such as magnesium aluminate spinel, single crystals. These crystals were irradiated with 220 MeV xenon ions at fluence ranging from 10 to 13 ions per square centimeters. We measured absorption spectrum, photoluminescence, Raman spectrum, and confocal luminescence along ion tracks and pulsed photoluminescence of these irradiated samples via fluence. The comprehensive analysis allows us to access changes in the crystals, structural and optical properties due to irradiation, contributing to a deeper understanding of defect formation and radiation response in spinel crystals. I continue our collaboration with Institute of Solid State Physics of Latvia. It's the main our collaboration for the Eurasian National University. And other collaborations, Institute of Physics, University of Tartu, Estonia, Institute of Nuclear Physics, Kazakhstan, Nazarbayev University, Kazakhstan, and joint Institute Nuclear Reactions, Dubna, Russia. Here you can see the collaboration Latvian scientists, Professor Katomin, Professor Manix, Professor Schwartz, also Manix, Ilse Manica. And Professor Katomin made significant contribution to the establishment of the scientific school of computation modeling. Yanis Manix and Ilse Manica advanced modern methods for studying nanoharness along the ion track in irradiated crystal. On this slide, you can see Kazakh PhD students doing internship at the Institute of Solid State Physics under the supervision of the Professor Anatoly Popov. Here you can see the Kazakhstan participate in the 20th International Conference on Luminescence Detectors and Transformers of Ionizing Radiation in Riga at 2024. The publication in this period from 2020 to 2024. 2024 is 2020 15, 2021 8, 2022 13, 2023 20 publications, 2024 24 publications. 15 publications. Some papers with Q1 publication together the Kazakhstan and Latvian scientists. So 5 top papers published during 2011 to 2020 in journals in Q1 and Q3 quarters. The articles together with Kadomin, Eglitis, Manix, Kurt Schwarz, also Manix, Anatoly Popov, Mironova Ulman, Robert Zabels, and others. My professional activities and services. I was the chair of the international workshop Radiation Effects in Insulators and Non-Metal Materials, which held in Astana 2014, and I was a co-chair of the conference 20th International Conference on Radiation Effects in Insulator, 2019 Astana at the Eurasian National University. Co-chair was Vladimir Skuratov. And the next conference, the 20th International Conference on Defects in Insulating Materials, 2024, where I was the co-chair together with Anatoly Popov. A professional membership. I am the member of the National Scientific Council of the Republic of Kazakhstan, the member of the Scientific Council of the Eurasian National University, the member of the Technical Scientific Council of the Eurasian National University. Thank you for recognizing my contribution to both scientific research and education. I have also greatly evaluated my collaboration with Latvian scientists, which has enriched our work in material science and education directed on the preparation of new PhD students and master students. Thank you for your attention.
Okay, thank you very much. You are coming from very rich country, and now the talk is open for questions. Could you please take away this presentation? We could see each other. I can't.
А мене не виключить?
Do you take away, please, this presentation. I can't see my colleagues asking for questions.
Может, закрыть его просто?
Okay, thank you. Please, questions? I can't see. Is somebody could tell from the Institute of Solid State Physics something about operation? It is very active. Is there somebody? Okay, if not, that thank you for presentation. That's very interesting for us, and we will be able to
Окей.
to evaluate your candidate in our next meetings. And so thank you for this. Now we will move to the next, our colleague Miroslav.
Yeah.
Is Miroslav here?
Yes, yes. Do you hear me?
Yeah, please try to be included in 10 minutes.
Yes, for sure. Thank you.
Thank you very much.
Thank you very much. So to share screen.
Yeah.
So is it okay?
Okay, very, very good.
Okay. Good afternoon, esteemed members of the Latvian Academy of Science. My name is Miroslavs D.Dramičaņins, and I'm honored to be considered for membership in this prestigious institution. I want to express my deepest gratitude for this opportunity to present my work and contributions to the field of luminescence. In addition, I would like to share my vision of how my work can further the mission of the Academy and contribute to the scientific community in Latvia and beyond. Sorry, this presentation is not, probably I didn't open the correct one, so it can be this one maybe. Okay.
Oh, that's
Sorry for this.
Yeah.
In my career, I have focused on luminescence, contributing to advancements in luminescent materials, mostly in lanthanide transition metal activated phosphorus for lighting and displays, in luminescence spectroscopy for characterization of materials, and in luminescence spectroscopy per se, and in luminescence thermometry, where I believe I have given the largest contribution. So to introduce my achievement, I will just firstly show you some scientific indicators. So far, I published one monograph, one book, 8 book chapters, 340 papers in journals indexed in the Scopus database. I have over 12,000 citations and a Hirsch index of, I believe, 53 now, according to Scopus database. I have 5 highly cited papers in Web of Science database, meaning that these 5 papers are among 1% by citation in their respective fields. I publish papers in high-impact journals such as Advanced Materials, Nature, Life Science and Applications, and so on. I'm listed on updated science author databases of standardized citation indicators, but it's commonly known nowadays as Stanford list. I am heavily involved in editorial work. I am associate editor of optical materials. I recently became editor of European Physical Journal ST. I am editorial board member of Physica B, Condensed Matter and Nanomaterials. I've been involved in many international and national projects. I've been project director of 14 international and 4 big national research projects, 2 Horizon projects, 1 NATO SPS, Science for Peace projects, several projects with the International Atomic Agency from Vienna. I was also mentor of 15 PhD theses and 4 Master of Science dissertations. I'm chairman of the ICOM conference. I've been involved in many bodies that are regulating scientific work in country and in European Union as well. I'm involved in teaching at the Faculty of Physics, University of Belgrade. I'm teaching 2 subjects, nanomaterials and physics in medicine and biology since 2009, but I'm mostly working in the institute as a research professor. I've been visiting professor at the University of Texas at Houston from 2017 to 2019. I'm distinguished foreign professor of science and engineering subjects at the School of Science in China since 2019. So this is briefly. But if I want to say something about my research and technological achievements, I will just point maybe 2 examples that I think that are important for my work, and that both of them are relatively recent. So basically in 2016, in the paper published in Advanced Materials, my group and I have introduced a novel new temperature sensor that utilize dysprosium emission in gadolinium 118 films that are fabricated by pulse laser deposition process. So what's interesting in this sensor is that it allows a measurement of the temperature in the intense high energy radiation fields, and also that it does not require any excitation because energy of the high energy radiation fields excites luminescence from the material, and we are then able remotely to measure temperature distribution inside, let's say, very dangerous and important object. So this concept enables simple technical solution to establish measuring system in our irradiation facility in my institute, and then with support of International Atomic Agency in Vienna, we install these systems also in Bucharest and Budapest in their radiation facilities, and now we are commercializing this sensor in collaboration with one domestic company. And also the second achievement I can, let's say, point out to paper in Light Science and Application, which is Nature journal, that we introduced a first type of luminescence thermometry probe that utilizes pentavalent manganese, which emits in near infrared, and it allows measurement in biological environment because the near infrared radiation is able to go through biological objects. It has a relatively high quantum efficiency for near infrared phosphorus, and we introduced temperature measurement with relatively high sensitivity. And after that, with my long-term collaboration with Wrocław University Institute of Low Temperature Physics in Wrocław, and very young and very capable group, we then further applied this thermometer in the biological environment. We published subsequent papers on these subjects, which are very well received in scientific community. As for cooperation with Latvia, I will divide it into past and current, and I hope future collaboration. So far, I have published 13 papers in journals with a high impact factor. We established a joint postdoctoral program. Unfortunately, only one candidate was part of this program, but we hope that it will be much more in the future. I've been a long-term reviewer and for scientific and innovation projects, bilateral projects submitted to the Latvian Council of Science for more than 60 projects, and also I've been involved in monitoring the progress of these projects, and we so far supported each other for conferences that we are organizing and in Latvia and Serbia. Several of them are listed here, but what is more important for me, I think, and from my colleagues from Institute of Physics in Latvia, that our past joint work and I think large efforts that we made so far open new avenues for our collaboration and mutual support, which is very important. At the moment, two of my colleagues from Institute of Solid State Physics are with me. We are trying to finalize one project and to submit it. So far we finalized the cost action application on luminescence thermometry network, and we are finalizing the application of Pathfinder for Pathfinder program on remote measurements of temperature in nuclear material storage facilities. We're also discussing application to Eureka program. The deadline is in December, but it will be, we need to find time because there are now open calls both in Latvia and Serbia. And in the past, we were helped by our colleagues from Latvia to work on this important European installation in Germany at LZA and in Max 4. And we also applied for new beam times recently. But we are now in position here to involve colleagues from Latvia into our newly granted European project. It's called Nephews. It supports big European support to use neutron and photon sources all around Europe, not just DESY and Max 4, but also Soleil in France, Grenoble, PSL in Switzerland. And tomorrow we have this important meeting jointly with the colleagues Anatolis and Vladimirs from Institute of Solid State Physics to finalize and to include Latvian community in this big project, because it, of course, what's important for us, all our scientists, that we have additional funding from the European project to go to these important facilities and to be financed our trips, our accommodation over there, some small money for research. So. And finally, of course, we are hoping for more high-quality papers. We need high-quality papers so that we bring our scientific level to more, both here in Serbia and also in Latvia, so that we can participate and we can get grants in the European Union. So I hope that I didn't take too much of your time.
You are very good. Thank you. Could you take away this?
Yes. Thank you.
For questions. May I see some questions? No, but not. I would like question a little bit unusual.
Yes.
Now you see it's Nobel Prize in Physics this year.
Yeah.
It's a surprise for many people, but background is solid state physics, as you see.
Yeah.
It's John. And what is your opinion about such attitude to the Nobel Prize in Physics?
We are we are too small to tell them what to do, you know. I think that it's good that we have such a huge awards. Sometimes they come very late after these findings are done. To be honest, I heard who won Nobel Prize in Chemistry this year. I don't know who won Nobel Prize this year for physics. To be honest, I didn't hear this news.
Okay, then it is future. Thank you very much.
Yeah, thank you so much.
Questions or not? No, I can't see questions. Thank you once more.
Yeah.
Good.
And thank you for your support.
Thank you.
Hope to see you.
Now the next is Michael. Good, please.
Yes,
Michael?
good afternoon. You hear me?
Yes, you are welcome.
Okay. You see my presentation?
Yeah.
Okay. Good afternoon to all. It is a great pleasure and honor for me to be considered and asked to present myself and some my topics of scientific activity before such eminent scientist. I am working as physicist, partially in chemistry, in Department of Theoretical Physics. I'm head of such a group, Jan Długosz University in Częstochowa, Poland. I complete many years ago my hosting university, Nicolaus Copernicus University, and my thesis was unexpected, and nobody believed for such possibility regarding superconductivity of at room temperature. It was a great work during my scientific life because we, with my supervisor, Professor Antonowicz, experimentally show opportunity of existing superconductivity in room temperature. Professor published a very important article in Nature, and up to present is very controversial. PhD thesis was focused also for not ordinary subject, coexistence of high temperature superconductivity and magnetic order. It was, the subject was before discovery of new superconductivity by Bednorz and Miller in 1986. Next, I obtained a habilitation, but habilitation was focused on nonlinear properties of ternary chalcogenide crystals. Is very important materials for infrared and mid-red spectroscopy. Here you can see in short way my some achievements. I published more than 200 papers in reputed journals, and the papers is focused on single crystals and material characterization, also optical materials. Here materials for mid and transparent in mid and infrared spectral range, nonlinear optics, and recently luminescence. Regarding structure, also nanomaterials and heterostructure. Here we investigate a special two-dimensional phase transition on some materials, influence of pressure on materials behavior, phase transition. As a practical application, some recent works is connected with solar cells materials, superconductivity, thermoelectricity, and batteries. Since chalcogenide materials are very wide spectrum of application, depends of prepared materials, because I very strongly collaborate with two Ukrainian university, Łódź University, Uzhgorod University, and Lviv University. I have attempt and also have opportunity to influence of produce new materials on demand for interesting properties. I have, during last 15 years, I have a little bit international collaboration. And one of most important is a collaboration with a Henkel Centrum Berlin when I performed several beam times utilizing two beam lines, one UV for application radiation source in spectral ellipsometry, and second far red for so-called infrared reflection technique for investigation some hyperfine structure of materials utilizing very weak radiation. When we go to a summary of my scientific publication, as I told, I published more 210 papers. I was a principal investigator in 6 bilateral projects. 8 projects were performed as synchrotron BESSY. I was reviewer more than 50 PhD theses, also have a very high activity as a reviewer in a high reputed journal. I many times was a reviewer and at present time also some Latvian scientist. My work was appreciated by authorities of some universities. It is some recent awards which I obtained. It is was connected with my long collaboration with on science and students exchange and collaboration and joint project. From 2021, I start a collaboration with a Latvian scientist. Since Institute of Semiconductor Physics is focused in partially on quantum chemistry calculation, especially for band structure calculation, predicting material properties, analyzing optical properties for different application. I think that such collaboration, except published up to present several papers, which give some additional opportunities. Since in my group we utilizing many methods which is a very convenient tool for testing quality of quantum chemistry calculation. I think about ellipsometry when we have dielectric function, for example, XPS when we came determining density of state of materials, optical properties, band gap, photoconductivity, also some trapping levels, etc., etc. And I hope that for such short time, we published such papers, and also we summarized some or achievements in such subject, which is results of joint collaboration, as a book chapter in very famous monograph edited by Professor Rush-Shilio. Also, I participate in joint on conference organized by Professor Popov, and he also was a co-author of several joint conference presentation. Except pure science, we also have some different kind of activities, like teaching activities. We see the Erasmus collaboration between University of Latvia and Jan Długoš University. Research, as I told, is focused at present on collaboration and cooperation with Institute of Solid State Physics, University of Latvia. Professor Anatoly Popov was a member of evaluation committee in doctoral procedure of my PhD student, Zafari Umar. He also will be invited as a reviewer of such thesis, and maybe during a good collaboration, we set up a so-called diploma system in PhD. It is a give opportunity to multiply students and start include to collaboration a young generation of scientists. Also, I thought I participate in some activities of Professor Popov. I also organized some international conference, and recently, last year, we organizing at my university 8th of generation conference between, it is called Polish, Ukrainian, Lithuanian conference on ferroelectric materials, and in next conference we would like officially invite group of Professor Popov to join us organizing such important for a scientific community event. Thank you for your attention. I hope that I keep in time.
Yes, thank you very much. Thank you. Could you take away this? We could see everybody, each other. Okay. Okay, thank you. Oh, there's question. Andris Ozols, please.
Thank you very much for your interesting report. You indeed have wide research in the different scientific directions, and among them nonlinear optical effects. I was interested in one of your papers, which I have read in your content, about second-order effects in zinc oxide nanocrystalline films.
Yes.
Also, I think gold and nanoparticles also were present there. But my question is mainly about crystallite size. How is the size of nanocrystals, zinc oxide nanocrystals, influence the effect, second-order effects? By the way, which type of second-order effects did you explore? Second harmonic generation or
yes, second harmonic generation. Because
so
yes,
about dependence of SHG efficiency on nanocrystalline size. Is it a monotonic, or it does not depend at all, or, and what is your idea?
Yes, because it was a very old paper. I think it was several years ago was published in nanotechnology. Yes, we investigate properties, different properties, nonlinear properties of materials, especially. Unfortunately, we not continue such research because we mostly focused on finding good materials for second harmonic generation, but in infrared spectral range, especially for monitoring environment. It was necessary for multiply frequency of CO2 laser, which broadcasting nearly 10 nanometers into spectral range 3 micrometers when is cover absorption spectral range of hazardous gases in atmosphere. But backing to your question, nanosizing give opportunity to changing formal structure of back materials. And for example, when ordinary materials is, for example, centrosymmetric, we believe when we go to nanosizing, it is ultra-thin film, I think a film on deep nanometers or nano-size crystals, we can breaking so-called most important limitation of second harmonic generating crystal, because it was crystals with centrosymmetry. But it is one of method of investigation. But unfortunately, due to some limitation of laboratories opportunities, because it is necessary to have a special laboratories to, for example, safe or divide nanocrystals on different sizes. It was difficult to continue such materials, but indeed, such old and one paper bring some interest of scientists, and I hope was idea for developing such introduced direction of nonlinear optics in a new road. It was many times in my life when I must changing subject of investigation, which was connected with some limitation and laboratories, limitation of opportunities in laboratories. But next we continue some such topics, but we amended nanocrystals into polymer matrix. It was a so-called composite materials, because we want to find opportunity to generate strong second harmonic generation without grow very expensive and very difficult for grow single crystals. But it is also one, as such my skills is also used with a collaboration with Institute of Semiconductor Physics, because group of collaborating with me scientists is focused in defect structure. Because except such unexpected phenomena when we, during nanocrystallization, obtain opportunity for second harmonic generation, we also, in another papers we publish when little bit imperfection, controlled imperfection of single crystals, improving nonlinear optical properties of materials. It was quite different when worse materials give some better opportunities. And also recently we use such technology for improving thermoelectric properties. When some unexpected and typical thinking is broken. For example, we increasing electric conductivity by substituting selenium, not by tellurium, is metallic, by sulfur with the electric. But due to some theoretical prediction, it was very exciting results, because so-called ZT, faculty of merit, grow 2 times. It was in my life many interesting unconventional attempts give very interesting results.
Okay, thank you.
Thank you very much.
Thank you. I can't see more questions. Thank you. And now we move to the next one. Jānis, varat latviski, ja gribat, bet droši vien angliski. Lūdzu, Jāni.
Yeah. Then, good afternoon, everyone. I hope you can hear me. I will share my screen. Okay.
Jā, lūdzu.
Okay.
Priekš.
All right, yeah. So good afternoon. Thank you for the possibility to be here and for the kind consideration. So my name is Jānis Timoshenko. Currently, I'm a group leader in the Fritz Haber Institute of the Max Planck Society in Berlin. So I got my PhD in 2015 in the University of Latvia in the field of solid-state physics. And then I moved as a postdoctoral researcher to New York, where I worked first at Yeshiva University and then in Stony Brook University together with Professor Anatoly Frenkel. And then since 2018, I'm in Berlin, first as a postdoc, now I'm a group leader there. But during all this period, I continued my close ties and collaborations with Latvia, in particular since 2021. I also have a teaching position in the Faculty of Physics and Mathematics, University of Latvia. So Fritz Haber Institute, to understand what's the focus of this organization, we can just look at the list of Nobel Prizes which were awarded to the scientists associated with FHI in the past. And if you look at these topics, and they range from development of X-ray diffraction and electron microscopy up to surface science and understanding the catalytic processes and the fundamental aspects of catalysis. So my contribution to all this story is the development of synchrotron-based methodology for understanding the structures of functional materials. In particular, we are working in hard X-ray regime mostly, and we are working with the design of experiment, execution of experiment, and also with the development of data analysis approaches. And in particular interest of us is the evolution of materials and how the structure and the properties of material change when the materials, functional materials and catalysts in particular, are exposed to the actual working conditions. So it's actually a very complicated process, and typically the catalysts can change quite dramatically when they're going from this as-prepared state to the final state, which is formed only when the catalysts are actually working. And these changes can take place on different length scales and time scales, so ranging from the changes in the chemical state and local atomic order up to changes in the crystallographical structure, surface morphology, and more macroscopic changes. And if you want to understand how the catalysts or other functional materials work and how to improve them, we need to really understand how these changes take place. And more importantly, maybe sometimes even to figure out how to steer these processes. And investigate these processes in a number of different systems, ranging from simple oxidation of metallic catalysts, going to the transition metal oxides, which are used as catalysts for electrochemical water splitting, where we study the formation of defective structures and follow crystallographical phase transitions, and going to even more advanced catalysts, such as single atom site catalysts, which actually are surprisingly dynamic systems, which can very much adapt to the actual working conditions. And for example, in recent work, we demonstrated that we can induce the formation of metallic clusters, which is completely reversible. So we can also form back as a single atom species by manipulating or electrochemical conditions and electrochemical protocols. So these examples are also examples of some of the challenges which we encounter in such studies. So first of all, as I mentioned, yes, these working materials are definitely not the same as the as-prepared materials, but also this active state of the material can be very different from the well-known standard materials which you can stabilize at ambient conditions. So they can have very unique structural motifs which are transiently present in these materials and have no analogs and more well-known reference materials. And finally, when we talk about the dynamic systems, we always need to be aware of that the catalysts are heterogeneous systems. So they're heterogeneous in space and time, which means that we have many different species coexisting in the catalyst. or another functional material. And some of these species are relevant for our activity, and some of them are just passive spectators. And we need to be able to, from the sample average data, somehow to decouple the contributions of these different species and understand what's important for the function and what's not. So to address this complex problem, we rely on a multimodal approach where we combine different techniques with different sensitivities. For example, from X-ray diffraction measurements, we can learn about long-range order and crystallographical order of the material, while from X-ray absorption measurements, we can learn about the chemical state of our metal atoms and the local order around them. And finally, when we combine these bulk-sensitive techniques with surface-sensitive techniques, such as X-ray absorption spectroscopy in soft X-ray range or optical spectroscopy, we can also learn about the active surface of a functional material. And then the more advanced techniques like X-ray emission spectroscopy or X-ray Raman spectroscopy can provide us with additional insight about the ligand structures and electronic structure of our material of interest. So one example of such multimodal projects, which is currently going on, is the construction of our own Max Planck Society-funded beamlight at Petra 3 synchrotron in Hamburg, where the goal is to develop a multimodal beamline where we can do simultaneously or quasi-simultaneously X-ray absorption, X-ray emission, X-ray diffraction, and small angle scattering experiments. And this beamline will be specifically dedicated to studies of catalysts. So you have all the necessary infrastructure, not only to carry out the synchrotron-based measurements, but also to characterize catalysts and combine different techniques in one unique experiment. And since we are funding this beamline, we will have also privileged access to it, which means that we will get approximately 2,800 of beam time hours per year for our Max Planck Society researchers, but importantly also for our collaborators. And I believe this project will be a really nice opportunity to establish new collaborations and find new ways how to work together for different groups who are willing to or interested in collaboration with us or other Max Planck institutes. And I'm happy to be one of the initiators of this project and coordinators of this large project. Now, regardless of what kind of spectroscopy we are talking about, one of the challenges remains data analysis. And this is a topic I was taught to be passionate about already during my studies in the Institute of Solid-State Physics and University of Latvia, and I continued these efforts through my career. And here, when we talk about data analysis, we need to distinguish between the direct problem and inverse data analysis problem. Direct problem means that if we know the structure of the material, we can calculate corresponding spectra. And it's a difficult problem, and dependently on the spectroscopy you want to use and dependently on your system, it can be more or easily treatable with different approximations and different computational tools, but in principle, it's solvable nowadays. The problem here is that in practice, we are more interested in the inverse problem, namely, if we know the spectrum of the material, how do we know what is the structure of the material? And this is a much more difficult problem because it's a ill-defined, ill-posed problem, so it has ambiguous solution, and you can only solve it if you have some additional knowledge about the material or impose some additional constraint. And one of the key developments in this field was that we recognized early on that one of the nice tools to address this inverse problem is to rely on machine learning methods. So here the idea is that we use these theoretical simulations, which I mentioned before, and to generate large database of spectra and the corresponding structure models. And now we can train mathematical model, for example, neural network, to recognize this relationship between the spectral features and some useful descriptors of the material structure. And in 2017, I first pioneered this approach on the example of interpretation of X-ray absorption spectroscopy data. Well, from the X-ray absorption narrow structure data from platinum nanoparticles, we were able, by using neural network method, to extract quantitative information about sizes and shapes of the nanoparticle. And later on, we have expanded this approach to other spectroscopies. For example, 1 year later, we applied this approach for the first time for the interpretation of extended X-ray absorption fine structure data, or EXAFs. And I'm glad to say that this was one of these nice examples where we collaborated with the scientists from Institute of Solid-State Physics in Latvia to get this very nice result. So the idea here is that we developed a neural network approach, which was trained again on theoretical models, but was now able to decipher this EXAF spectra for metallic iron and extract the information about the radial distribution function or the bond length distribution of in this material. And by using this neural network approach, we were able to track the phase transition in the iron as a function of temperature and to monitor how the BCC structure of iron is converted into the FCC structure of iron. So since then, this method has been applied to a very broad range of different systems. So we have a patent, we have received award from International X-ray Absorption Society for the development of this approach. But importantly, that it's now available to the community and can be applied to different spectroscopies for studies of metals, alloys, oxides, different heterogeneous materials, and importantly also for working materials, so working catalysts under actual working conditions. And just one the example from our such a recent work, which I'm still pretty much excited about, is the application of this approach for the understanding the structures of transition metal oxide catalysts, which are used as a catalyst for electrochemical water splitting, where we demonstrated that from the sample average spectroscopic data, which were averaged over the entire sample over all metal species which are present in the sample, neural network approach can able to independently extract information about the changes around tetrahedrally and octahedrally coordinated metal sites. So we demonstrated that these sites evolve differently. And by using this tool, we were able to rationalize a complex map of different species and different phases coexisting in these oxide catalysts and co-evolving under reaction conditions, and could identify the active species and see how these active species evolve as a function of the OR catalytic protocol. Yeah, so with that, with this example, I would like to conclude. I would just like acknowledge some of the people with whom I collaborated in the past and continue to collaborate now, and without whose contribution I would not be able to be here and present in front of you. I thank again for your consideration for this position, and I thank you for your attention.
Thank you for this. Questions, please? Could you take away this? Okay, I can see. Oh, results, Andris. Okay, go ahead.
Sorry, I cannot hear you.
Oh, I would like to repeat the question of Professor Silic, which he gave to the first speaker, no, to the second speaker, about this year's Nobel Prize. Why? Because you also mentioned machine learning for interpreting of spectrum. So what is your opinion? Did the Nobel Committee act correctly when they gave the Nobel Prize in Physics for machine learning? Thank you.
So I can just refer to one of my first slides in my presentation where I showed that in the past Nobel Prizes were awarded also for things like development of X-ray diffraction method or development of electron microscopy. So really methodological developments which provided researchers with new tools for understanding materials and complex processes in these materials. And in this regard, I think it's just another tool that we have now, thanks to these neural networks, which provides us with new possibilities to look at the experimental data and learn something about the material. So in this regard, I think it fits very well with the past history of Nobel Prize awards. And of course, we can discuss whether all the right people were acknowledged, because huge communities are working on this problem right now and development of these machine learning methods. But in general, I think it was quite reasonable decision, in my opinion.
Thank you.
Okay, thank you. Miroslav, you would like to tell something also?
Yes, so maybe I can now answer, because I took liberty to check who won Nobel Prize for this year, for which topic. And actually, I'm using some tools from machine learning in my research, and I can say that these are wonderful tools, and they will be helping us a lot, scientists. But there is one thing, it's a paradigm, which means that it's kind of learning. So generally what we are doing, we have frames of our own knowledge, human knowledge, in which we give a machine to learn. So basically it can find only new things which are in this frame. So it can help, but it cannot go beyond the current knowledge that we already established. So in my opinion, now it's not a good decision.
Okay, thank you. We will discuss, I hope, also in our division or in academy about all Nobel Prizes, because this thing is now very, very popular.
Yeah. Thank you.
Okay.
Thank you.
Thank you. More questions? No? Okay, then I would like to thank everybody who take a part in this meeting, giving reports. And I would like to tell a little bit about the next steps. The next steps is such that first of all of candidates to all positions, full members, corresponding members, foreign members, first of all will be evaluated in our division by our colleagues. That must be done till the end of this month. Then there will be developed an Academy of Science Special Commission, which will also discuss and consisting of the chairman of divisions and other people. There will be discussion, and I am very happy to share all this information. I will be able to tell more about your work. And after that, there is voting in Senate, but it is not the final voting. The final voting is in full meeting of all members of Academy of Science. And that will be in the 21st of November. Therefore, you will know your next position after the 21st of November. That is this procedure. Would you like to ask some question about this procedure? No? You could follow. You could contact with colleagues and follow all this procedure. Now, once more, thank you very much. And now, tagad es gribētu jautāt, vai vēl dažādos ir kādi jautājumi. I can't see more questions. We are good in time. Once more, thank you very much. And we will have one more meeting in 1 week, in 23rd in October. And after that, this whole procedure will start, this evaluation. And we will need once more to do that by our division till the end of this month. Okay, thank you, and luck for everybody. Good luck.